We're going to go over the sum and difference identities for sine and cosine. Again, these rules get used quite a bit in calculus, sometimes more in Calc 2 than Calc 1. In trig, we're just trying to learn the rules. You really learn to appreciate them when you start to use them in calculus class. First, we're going to talk about the rule for cosine of the sum of two angles, so cosine of A plus B. All textbooks have a proof, and your textbook does have this proof worked out. I'm not going to work out the whole proof, but the idea is if you have some angle A, so A is the smaller angle here, and then you have a second angle B, and I made B bigger than angle A, but it really doesn't matter. One will be bigger than the other, usually. Then if you add A to B, so picture taking this angle and stacking it outside of B, this point here represents the terminal point of A plus B. Well, the distance between these 2 points should be the same as the distance between these 2 points, because the angle from here to here should be A, because that angle should be A plus B minus B, which would leave you angle A. And that's the basis of the proof. If you work through the geometry and the algebra of showing that these 2 points are equivalent to these 2 points, you end up getting the sum rule for cosine of A plus B. And that rule is that cosine of the sum of two angles is equal to cosine of the first angle times cosine of the second angle minus sine of the first angle times sine of the second angle. So for example, if I had cosine of 12 degrees plus 20 degrees, that would be equal to cosine of 12 degrees times cosine of 20 degrees minus sine of 12 degrees times sine of 20 degrees. Now I know when you have specific angles, it seems like, well, why can't you just add 12 and 20 together and get 32 and then use your calculator to get cosine of 32? If that's really the situation you had, that's what you would do. But sometimes the angles are represented by variables, and you are solving an equation or doing some other proof, and you don't have specific numbers to plug in. So that's usually when the identities come to our rescue. Sine also has a similar rule. It's sine of A plus B is equal to sine of the first angle times cosine of the second angle plus sine of the second angle times cosine of the first angle. In terms of trying to keep these rules straight, you might want to recognize that for cosine, the same functions kind of stick together. So they're like co-workers. They kind of stick together. So cosine, cosine, sine, sine, and then there's a subtraction. For sine, the sine stays the same. When I'm adding the angles, I add these expressions, so the sine, the SIGN, stays the same, but I have different functions here. Sine of A, cosine of B, sine of B, cosine of A. That's just a little mnemonic device to help you. Now, these identities can be used to actually prove other ones. So, for example, if you think about cosine of 2A, 2 times A means A plus A. And so if I use that in this rule up here, I get cosine of A times cosine of the second angle, but the second angle is also A. And then minus sine of A times sine of the second angle, but the second angle is also A. So that actually gives us cosine squared of angle A minus sine squared of angle A. And so that's one of the identities for cosine of 2a. I say one of the identities because you could actually rewrite this by using the Pythagorean identity. Cosine squared is equivalent to 1 minus sine squared. So if I rewrote cosine squared as 1 minus sine squared, I would end up with this expression. And 1 minus sine squared minus another sine squared gives me 1 minus 2 times sine squared. And so that is a second expression that is equivalent to cosine of 2a. Sine squared is equal to 1 minus cosine squared. So you could do the same thing and you could write down cosine squared, but then rewrite sine squared as 1 minus cosine squared. And that would equal cosine of 2a. And then if you distribute the minus sign, I'm subtracting 1 and I'm subtracting minus cosine. So I would get cosine squared minus 1 plus cosine squared. And notice I have cosine squared plus another cosine squared. So that gives me 2 cosine squared a minus 1 is equal to cosine of 2a. So I have actually 3 different expressions that could all be used as an identity for cosine of 2a. I have this expression, cosine squared minus sine squared is equal to cosine of 2a. I have this expression, 1 minus 2 sine squared a is equal to cosine of 2a. And I have this expression, 2 cosine squared minus 1 is equal to cosine of 2a. Now for sine, you don't have all 3 different versions, but you could do a similar proof. Sine of 2a would be sine of a plus a, and following this rule up here, I would get sine of a times cosine of the second angle, but the second angle is a, plus sine of the second angle, but the second angle is a, times cosine of a. And notice this is the same as that. So sine of 2a is equal to 2 times sine of a cosine of a. And that is the double angle formula for sine.